Hello, my name is Johan Newmoptical. Today I want to talk about the topic of the displacement method when it comes to calculating systems that are statically indeterminate. In the previous video, we saw how to calculate such systems with the force method, and now we're gonna look at another one, and that's the displacement method. Like for the previous video, I also got a German video already on this topic. You can watch that one to see different examples and yeah, to have the German version if you're interested into that. And this one is the English version for German speaking people to get like the English expression, let's say, and for English speaking people to also know like what's about. But basically those are stuff that you probably did in your bachelor, so that's gonna be a revision for you guys if you're master students, and I hope it will help students in the bachelor to get the stuff a little bit more accurately if it wasn't possible during the lectures. So let's just pick a statically determinate a statically indeterminate system. I'm gonna take this one. So we can check pretty easily that it's just statically indeterminate with our formula a plus t minus 3 times n. What do we have here? For A we have 3 reaction forces at the clamp support plus 1 for the holder support, that's 4. Then the hinge reactions, we got none of them, we only have one body here, so 0 hinge. Minus 3 times 1 body, that's 1. The system is statically indeterminate to the degree of 1. That information will have actually been necessary for the force method. But here we're using the displacement method, and in the displacement method, we're not interested in how many forces are too much or how many equations are actually necessary, and do we have as many unknowns as available equations. Here what we actually want to do is we want to make sure that all the displacement are known. So in the force method, we want to make sure that all the forces are known, that all the reactions are known, and if we have some forces that we cannot calculate because the total number of unknown is more than the total number of equations we can write, we take those supplementary unknowns out first in this way, that we actually get a statically determinate system or a zero system on which we're going to apply the external load first, calculate the deformation, moment, shear forces, normal force distribution, and on that system later apply the single loads or moments that we removed first to make that system statically determinate, and compute again normal, shear forces, and moment distribution, and then calculate the deformation that are occurring and look out for a compatibility to get those unknown forces. Now, in the case of the displacement method, we're actually going to look for displacement. So what we want here is not to know all the forces, but actually to know all the displacement. And by knowing all the displacement, we want to actually give them a known value, and that value is 0. Basically, we want to restrain the displacement that we have here. So when we look at a node in the plane in 2D, we basically got 3 possible degree of freedom. That node can move in the x direction, move in the y direction, or we can have a rotation around that node. So we want to make sure in each case that those nodes cannot move. We have to take into consideration here the actual rigidity. Is it infinite or not? It's gonna make a lot of difference. We can actually see that if a beam, for example, got an actual rigidity of infinity, it means that it's enough for me to restrict that beam from moving in its length direction on only one side, and alone with that restriction, we know already that the whole beam cannot, the other node, a beam got two nodes, like two extremities. If we just restrict the movement, the displacement of one node in the length direction of the beam, we can say automatically that the other node cannot move either, because EA is equal to infinity. The actual rigidity is equal to infinity. But if EA is constant, restricting one node, restricting the movement of one node in the length direction doesn't mean that the other node cannot move in the length direction, because my beam can elongate. I can have some elongation. So depending on whether EA is equal to infinity or not, we might need more or less restrictions. So for this exercise, we're going to assume that EA is equal to infinity. And what I can tell you already is that every time that we got a frame corner, or we have two partial beams coming in contact with another with a specific angle between them, we need the restriction of the rotation, and we're going to draw it with a square like this and shade it a little bit. That is to restrict the rotation of that node. Now, what else is possible here? This node, in a general way, could move to the left or move to the right. We also need to make sure that that's not possible. This node goes in a general way to move upward or move downward in a general way. In a general case. But here, EA is equal to infinity. It means that this beam here can neither elongate nor get shortened. So a movement here, displacement here in the vertical direction is not possible, because this lower node is already clamped, like it's already restricted, it's already blocked. A movement in this vertical direction is not possible, and our beam cannot elongate, okay, or get shorter. So this node cannot move in the vertical direction at all. A movement in the horizontal direction is still possible though, so we will need a restriction. But and a very easy way to know if someone needs extra restriction or not. For the moment, is quite obvious. Like at every frame corner, you need such restriction, or every time that there's a sudden change in the load, you also need such restriction, because it's gonna create a jump in moment. So if suddenly here I had this, okay, not a single load, but if suddenly I had a different value of the shear of the distributed load here, then I would have needed to put a restriction, a rotational restriction there, and rotational restriction should also come, automatically with a support beneath. We cannot just leave the rotational restriction like this in the air. You cannot do any calculation with that. So moving forward here, how do we know where do we need those support restriction? Like I said here, we're gonna need something like this to restrict the horizontal displacement. But how do we know in a general way where we need those support restriction? What we do is we use the following. We use a Hinge diagram. So where are support restriction needed? So the hinge diagram is what we use. How do you create a hinge diagram? We get the figure, the system, as it was given, and then we just transform every node into hinge. So this here is a clamp support, but if I put a hinge there now, this becomes actually pin support. You can just throw the hinge there. Here, this frame that was actually transferring normal forces, shear forces, and bending moment now becomes receive a hinge there and cannot like transfer the moment anymore. And over here, this was basically already a hinge. Like when you just have like the hollow support, it's already a hinge there. So that's what we got. This is our hinge figure. Now we're gonna make sure that our hinge figure is statically determinate. So if some supports are missing here, we're gonna need to add them and make sure that the system is statically determinate. Some tools to help here are definitely the pole plan or pole construction. Pole plan, pole construction. I also have a video to that. It's called Bauschatzige Grundlagen Pole Plan. You can see that. Watch it. So let's do it in an easy way. First, let's check if the system is statically determinate or not. One might actually easily say that this system is moving. We are expecting a 3-hinge diagram, for example. This is one of the possible form of the possible known statically determinate form that someone might think about at this point, and it would require a pin support here, a second pin support there, and then 2 holes joined together with 1 hinge. But here we have 1 pin support, but the other support is not a pin support, it's a hollow support. So 1 reaction is missing there, and for that this system kinematic. But we can check that with our formula. A plus D minus 3G, minus 3, how did I call that? 3N. And I call G the degree of such indeterminacy. For A here, we will have 2. The moment is not there anymore. And that is for the pin support, and then 1 for the hollow support. So a total of 3. We have 2 bodies now joined by a hinge, 1 hinge, because we got 2 bodies joined at that hinge minus 1, so 1 hinge. One hinge got, each hinge got 2 hinge reactions, so it's 1 times 2. Those are 2 hinge reactions minus 3 times 1, 3 times 2 bodies. So we got 5 minus 6, that's minus 1. So this system is actually not statically indeterminate, it's kinematic with 1 degree of freedom. Of course, I'm doing this really step by step. When we're working with the hinge figure, it's a step of the exercise where we actually don't want to waste a lot of time. So if someone can see directly that it's kinematic and see exactly what's necessary there for the system not to be moving and to become statically determinate, someone can just do that directly without showing all the stuff. kinematic with 1 degree of freedom. So we need to add 1 restriction here. And like I said before, a possible form here is, basically it's the only thing we can do. Oh wait, is it? No, it's not the only thing we can do. We can put it here, for example. That's one possibility. This system becomes like a 3-hinge diagram. It becomes basically something like this. What we can also do, another alternative, is to put the Hinge support actually here. To put the restriction here, the extra restriction there. And then put it like this. At this point, it definitely doesn't matter because this support needs to take a certain force, and that force is gonna be the same. Doesn't matter if it's at this end of that beam or at the left end or at the right end, because on that beam in the length direction we don't have any load, so it's just gonna be a constant normal force in there. It really doesn't matter. There's as good as no difference between those two systems. Yeah, so I'm gonna choose this system. You can choose that one or that one, it doesn't matter. I'm just gonna choose this one, the first one I came up with, and I'm gonna continue with that. So what does that tell me? It means my system there, actually I put the restriction here already, but it doesn't matter. I can still use the other system. Like I said, you can still use this system here. So now what we got here is a system that's kinematically determinate. That's how we call it. What's a kinematically determinate system? It's basically a system in which we know all the deformations that occur, or even if we don't know them completely, even if we don't know like all of them, we might still be able to calculate all the values of moment, shear forces and stuff thanks to our tables. So in a pure sense of the term, a kinematic determinate system will be a system in which all nodes got their, in the plane, all nodes got their 3 degree of freedom restricted. So all the rotations are restricted, so much be here. It's clamped, so the rotation is restricted, the horizontal and the vertical deformations or displacement are restricted. The same here. And here I just restricted the rotation, but the vertical and horizontal displacement are also automatically restricted if we suppose that the actual rigidity is equal to 0. If the actual rigidity is not equal to 0, if EA here, for example, is constant, then I need to take into account the fact that this beam here might be able to get longer, so I need to restrict that vertical displacement, and this one too might be able to get longer. I need to restrict these two. Of course, here in both cases I was assuming that the flexural rigidity is constant, because if the flexural rigidity of one of those beams, for example, is infinite, then it would mean that that beam cannot have any deflection, cannot bend at all. So yeah, you should just take it into consideration. If, for example, this beam here cannot bend, it means I don't even need this restriction in the vertical direction. And if the vertical one here cannot bend, then I don't need this restriction in the horizontal direction. But don't really have this case in in exercises, generally the flexural rigidity is just constant. And yeah, that's basically it. Or the flexural stiffness, you can also call it like that. Yeah, so moving forward, what do we actually do? That was just, this got nothing to do with our exercise. I was just showing what should actually be the case in a when we wholly speaking about kinematically determinate system. So this is our system here, the kinematically determinate one, and we put on it the external load. It's pretty similar to what we do in the force method. The only difference here is we didn't remove the forces that were too much, let's say. We instead added some restriction to remove unknown rotations or unknown displacement. By adding the restriction, we make sure that we know their value or that they are zero. For example, by adding the restriction here, we make sure that we know the value of the rotation of this node and it's zero for the moment, of course. And then later what we're gonna do is we're gonna say, okay, in reality, I got no restriction at this node. So this node actually got some value, and we're gonna rotate that node with an angle of 1, a unit rotation. And then our objective is going to be like to find out how big is that rotation actually, because it's not really one was just like a unit value to have an idea of which is what's going to happen, how the moment distribution going to looks like and stuff. And then we're going to find out how big is actually that rotation. And when we find everything out, we're going to use a kind of compatibility again. In the case of the force method, the compatibility had something to do with the geometry. We said, okay, first we remove those forces here, then we put them back. We see the displacement that we have with the external load, the displacement that we have with the forces that we removed, and then we make sure that there's a compatibility according to the geometry. For example, maybe the displacement of a node is supposed to be 0. Maybe a slope is supposed to remain 0 or have a certain value. Now, in the case of the displacement method, what we do, the compatibility had nothing to do with the geometry, but rather something to do with the forces. We put some restraints that are actually not there. By putting those restraints, and especially in the unit cases when we're going to turn them, we're going to create some moments, some extra moments, not just moments, but jump in moments, for example, or jumps in shear forces or jumps in normal forces that are not supposed to be there. And the compatibility we use here is rather a kind of equilibrium. We're basically just making sure that the moment, for example, left from the node and right from the node is gonna be the same. Basically, we're making sure that at the end, there's nothing strange happening in the moment distribution. If there's no jump to be expected, there should not be a jump. Because when we have something like this, okay, I'm going to explain this further as we move forward. I'm going to show you what I would call here incompatibility when it comes to the forces, and we're going to see which equation needs to be written or which condition needs to be fulfilled in order for the system to meet its compatibility when it comes to the forces. So, and like I said here, I'm just using the compatibility for people to see like the link with the force method, but here is basically just gonna be like equilibrium between forces. So let's move forward. So this is gonna be our, let's call it 0 state or 0 case, or yeah. We put the external load on our system and we calculate the forces, the moment distribution. So what we're gonna get, those values, those systems here that we have are statically indeterminate. This system here is basically this one. And the system, this vertical system here is basically this one. And you can see that the horizontal system here got some load on it. And the vertical one got nothing on it. So what we're gonna have is we're gonna find some values. Something that I need to say here too. We got different conventions here when it comes to the internal forces. Normally in the force method, let's call it Fm, the internal forces look like this. On the right side, the normal forces going out, the shear forces going down, and the moment in that direction, M, N, and V. And on the negative phase, we had shear forces going up, normal forces going out again, and the moment in this direction. But now for the displacement method, the internal forces look like this. The right side is the same, and the left side is exactly completely similar to the right side. No change at all. That's what's new here. So the right side is as it's always been, but the left side is the opposite, something else. That's what needs to be taken into consideration here. Can lead to some mistakes. So the values, we got them actually from tables, like in the Schneider bar table, we can also get them, and the values also, they're very depending on whether we're calculating in with the second order theory or the first order theory. The calculation I want to do here are with the first order theory. That you can move. Yeah, so we got some system here. This is a beam that's clamped on both sides, and no, what is this? I know this is like the copy tables. I'm sorry, it's not what I thought. Yeah, we have this system, for example, is a beam clamped on one side and paint supported on the other side, and we have a certain load, and we can see what are the forces, what are the moments. We have different load cases there. We can also have the case clamp on both sides and with different loads, and we can directly read from tables what are the values. Okay, those are the values. What I've just shown are the values in the first order theory. For the second order theory, we first need to calculate in the first order theory the normal forces that are present in those beams, or just estimate the value of those normal forces. Then from those normal forces, calculate the value of alpha, the slenderness. It's L times the square root of S, the normal force that we estimated or calculated in with the first order theory, divided by EI, Young's modulus I, second moment of inertia. Okay, and then the formulas for the moments and stuff got something to do with alpha. And yeah, basically. So let's keep going here. Something else, this element here, beam clamp on both sides, is called basic element 1. It's just a convention. And this one here is called basic element 2. We can also have it with the pin support on the left. So one of them is called basic element 2A and the other one is basic element 2B. I think it's this one 2A and that one 2B, but it doesn't really matter. Formulas for those systems are actually available in tables. When it comes to theory of second order, a simple lever arm is actually a simple cantilever beam is actually also available. So I'm just showing here the load case, distributed load, but we have different load cases with single loads or single moments and stuff like that. Okay, so the values here, the moment is going to be 0, and here is basically gonna have the value of QL squared divided by 8. Positive, that's actually a value we calculated in a previous exercise. This value here, it was minus 1/8 of QL squared, but the moment was drawn in the not in the positive direction of the first method. But now we have like the displacement method, and it's on the left side of the beam, is the other way around, so there is a positive value of the moment. And for the vertical beam here, we got like no moments at all. It's not loaded at all. Okay, and what do we want to compute here? What do we want to calculate here? The forces here, set, I can call this one set 2, 0. Choose the position 2. I define this one as position 2, and for me the position 1 is going to be there where I've restricted the moment, and the 0 here just indicates that we're in the 0 state. So the external the load is the external load, and we want to compute those values. The Z10 value is going to be calculated through equilibrium on this node. So what do we have there? I have the Z10 as moment. I have the QL square, 1/8 of QL squared, with the principle of axial here, axial. The moment here acting on this beam is also going to act on this rotational restriction in the other direction. So this is QL squared divided by 8. Okay, and with that, with some of the moment around this point, we can call it whatever we want. We find out that Z10 is equal to QL squared divided by 8. Another thing we need to compute here is the value of Z20, and to calculate this value, we can basically say the following: that the beam over here, this one, is not loaded at all, meaning that the shear forces here are equal to 0, and the shear force present here would have been the normal force in this beam, and by the same occasion the value of the support reaction here. So that support reaction got the value 0. We can use that argumentation. But how do we normally get those support forces? We're going to use the principle of virtual displacement. It works like this. We need our hinge figure again, but not with the support. So we don't want the hinge figure to become a such a determinate system. We let the hinge figure as it was from the very beginning. And if we had to put different restriction to make it statically determinate, we're just gonna make sure that we remove the restriction for this support. We just had, let's say we had put it like 1,000 different supports restriction to make it statically determinate. Now from those 1,000 different supports, we're just gonna remove this one to make sure that it only got 1 degree of freedom and that it can move in the direction of this force. Moving to the left or moving to the right, it doesn't really matter. We're going to take that into consideration when computing the value of the work. So what I do now is I remove that support. So for my statically determinate system, or for my statically determinate the hinge figure, I remove the restriction in the wanted at the position of the wanted force that we want to calculate. So the system we have here is kinematic. That was actually the value it had from the very beginning. But it doesn't matter when we have a statute determinate system. If I remove a support, it's become kinematic with 1 degree of freedom. And now what we want to find out is how is this system gonna move? What are the displacement that can occur here? Like if I just move one node in one direction, how is the whole system gonna move? And to do that, we need pole plan construction. Like I said, there's a video to that where I really go deep into the pole plan, how it's done, what do we need. I'm still gonna do this example here, but it's pretty simple. So to make sure that you got like all the tools necessary to be able to construct every pole plan, we really recommend you to listen to that video over there. So what do we have here? We have 2 bodies, this vertical hod and that horizontal one. The vertical hod got a pin support here. That's really nice. That means that's automatically the main pole of that body. That's the point, the pole around which this body is gonna turn when he's moving. Every body, when he's moving, is basically turning around a point, and that point, that pole is his main pole. Okay, we call it main pole. When a body is bounded to a pin support, that pin support is automatically the main pole of that body. So here for the body 1, we got already the main pole of body 1. It's here exactly the position of the pin support. For body 2, we still need to find out where that main pole is. Something else that we need to know here is when we look at the Hollow support, this hollow support in this position can move horizontally. And before I go a little bit deeper in what it means for us, I'm gonna show here how a body actually moves around its main pole. Let's say I got a bar here, yeah, and that bar is moving around this pin support. At the symmetry of that bar, have a node A. A is when A is moving, A is turning around the main pole 1, 0, describing a circular movement. If we were working with big deformations, we're working here with small deformations, means the displacement of A is actually tangential to the binding line between the main pole and the point A itself. It's tangential to that circular curve or orthogonal to the binding line between the main pole and the point A itself. So this 90-degree angle, this is the tangent, and the small movement is actually perpendicular to that binding line. And that binding line can be called pole ray, actually, like it's like a ray, like as if the pole was the sun and it's just sending sun rays like all over the place. So this binding line is called a ray, and the displacement here is the displacement that's occurring is perpendicular to the ray. And every point of a body, when that body is moving, is rotating around the main pole with the same angle. Every point of the body, while the body is moving, is rotating around the main pole of that body with the same angle. That means not only I'm not only talking about the absolute value of the angle here, I'm also talking about the rotation sign, like the rotation, about the sense of the rotation. Like, is it clockwise or counterclockwise? Every point is rotating with the same value of the angle in that same direction and around that same main pole or primary pole. You can call it, also call it primary pole if you want. Yeah. Now, when it comes to a hollow support, we're gonna use this information backwards. With a hollow support, we know already a body, let's say random body, is connected, bound to a hollow support. We know already how that hollow support can move. And we know that when a body moves, every part of that body is actually rotating against around a point, and that point is like the main pole or the primary pole. If we know already that this body is moving in this direction, in this horizontal direction, let's say, then we know that perpendicular to that movement direction, we have the pole A, and in the direction of that pole A, we have our pole somewhere over there. Somewhere on that direction, might be above there or below, but somewhere on that line, we have a pole. So when I see a hollow support like this, I can directly say that in the direction of this, to make it easy, let's say in the direction of the hollow support force, we have a pole, the pole of the connected body. We can call it L2 for line 2. On this line, we have the primary pole of body 2, somewhere on that line. Now, what do we have here? This hinge, a hinge between two bodies, is automatically a so-called secondary pole. The secondary pole, we noted like 1, 2, that's notation for it. It's like the primary pole is the point around which the body turns when it's moving. Every point of the body is rotating around that pole, around that point, around that primary pole. The secondary pole is more like a point that can move on its own. Okay, something I should have also said is that the primary pole is not moving, it's never moving, at least in static. In dynamic, we can see situations where we say, okay, we have a pole that's moving, we have momentary pole, like for 1 second or 1 split second, a pole is somewhere, and then after a certain time, the pole is somewhere else, and the pole is actually moving. But in static, that pole is not moving. The primary pole is not moving, but the secondary pole is, or the secondary pole can. Actually, if a secondary pole is not moving, then it's basically a primary pole, but that's something else. So the secondary pole is basically a point around which the two bodies have relative rotations. Let's say they rotate relatively around that pole, and that pole can also be moving around. Just to have a little bit of a conception what that is. And now there are certain rules when it comes to pole plan construction. It's a little bit all over the place here. I can't really like go too deep in there because there's a specific video for that, and if I go too deep in here, this is also gonna be too long. The wolf is gonna be too long. Anyway, there are like 2 lines that needs to be known when it comes to the pole plan construction. 2 primary poles, for example 1 0 2 0, and the according secondary pole 1 2 need to be on the same line, should be on the same line for the pole plan construction to be fulfilled, let's say. And there's a second line again with 3 secondary pole, the secondary pole 1 2, the secondary pole 1 3, and the secondary pole 2 3. You can see that there's actually logic in there. 1 and 2, 1 and 3, and the only couple that's missing is 2 and 3. Should also be on the same line. On the same line. If a whole pole plan construction is done without any contradiction to all those holes, all those lines, then the system is kinematic. So actually, if we don't want a system to be kinematic, we need to find contradiction. We need to find, contradiction to those holes. Basically, to be sure that the system is not kinematic, we need to find contradictions to the primary pole of each body. So what is this rule telling us? 1 0, 1 2, and 2 0 should be on the same line. I have 1 0 here already. I have 1 2 there. It means on this line I should have 2 0. So this is line 2. But we got line 2 here already. If they were crossing at a certain point, we would say, okay, the primary pole of body 2 should be on this line, the primary pole of body 2 should be on that line too. Both lines are crossing at this point, so that point is the primary pole of body 2. In this case, the lines that we have are both parallel. What we're gonna say is not that they don't cross, but we say is that they're gonna cross somewhere in infinity. Like the assumption that we take also for sun rays, they like we assume when they're on the earth that they're actually parallel to each other. Okay, let's say the sun is over there and the earth is here. We assume that the sun rays are actually, when they come here, they're parallel. Or maybe my assumption is wrong, but I think that's what we do in physics. But actually they come somewhere from, okay, it's an extended source of, it's an extended light source, but basically, let's say that they come from the same point, but because the distance is so big, when you have to the earth, we have the impression that they're parallel. So we use the same logic here, and we say, okay, here they're parallel, but somewhere in infinity they actually cross. Okay, so we say that the primary pole here is in that direction in infinity. That's the position of the primary pole of 2, 0. Some additional information need to be given here on primary poles. A contradiction on a primary pole, I'm going to call it PM. A contradiction on a primary pole means that the associated body is not moving. That body is fixed. So if I have a contradiction, for example, on 2, 0, it means that the body is fixed. What is a contradiction? A pole is uniquely defined. I cannot have two different positions for a pole. If I find something like that, it's a contradiction. I write it here, poles are uniquely defined. Examples for all of those points I'm just like throwing up here in that video I talk about. I cannot go through all of that now. I'm really sorry for that. All poles are uniquely defined. Doesn't matter if you're talking about primary poles or secondary poles. Now a primary pole, if we got a contradiction in primary pole, it means that the considered body is fixed. For example, if you have a contradiction on primary pole 2, 0, it means that body 2 is fixed, so it's not moving. A contradiction on a secondary pole, primary pole, secondary pole, for example, 1, 2, means that 1 and 2 are the same body. 1 and 2 are the same body. So if somewhere I had 2.0, I can already say that 2.0 is the same as 1.0 and stuff like that. When a body is fixed, if I had something like 1.2, let's say I had a secondary pole 1.2, so it was like a pole or a node between body 1 and body 2. Both of them could turn around that point, kind of, not really, because they actually turn around the primary poles. They could kind of turn around that node, that point, and that point could move. But now we prove, for example, that body 1 is not moving. So we have, for example, we have found a contradiction on the primary pole of body 1. It means that body 1 is not moving. It means that that relative rotation point is not moving anymore. So it's just a fixed point around which body 2 can move. So what does that mean? That point has become a primary pole for body 2. So if we found out that the primary pole, that we have a contradiction on primary pole of 1, 0 of body 1, for example, meaning that body 1 is not moving anymore. 1, 2, what was a secondary pole, is going to become a primary pole for body 2. 2, 0. I just tried to explain it really quickly right now. Hope it was clear. First, it was a relative rotation point that could move, but now we found out that one body can actually not move. It means that that relative rotation point is actually fixed and only the other bodies move around it. So it's actually a primary pole and not a secondary pole. That's what I was explaining here quickly, but again, I'm going to say it for the last time, watch this video. So coming back here, I won't do any extra course anymore here. This is 1 0, this is 1 2 2 0. The primary pole is found and is in infinity. Primary pole in infinity means the following. Primary pole in infinity means that that body, the considered body, got a pure translation. It's moving and got a pure translation. Pure translation. And the direction of the translation is orthogonal to the direction of the pole. So the pole is in this direction in infinity, the body is going to move orthogonally to that direction. That's a translation means that every point is just moving with the same value to the left or to the right, whatever, or above and down. In this case, it's going to be laterally with the same value. And a secondary pole in infinity. Secondary pole in infinity means that both bodies 1 and 2 are rotating with the same angle. We're not saying that they're rotating around the same pole, we're just saying they're rotating with the same angle. So secondary pole in infinity, for example, 1 2 in infinity means that phi 1, the rotation angle of body 1, is equal to phi 2, the rotation angle of body 2. Yeah, I think we're gonna be interrupted soon because I'm not gonna have enough memory. I'm still gonna push on this though. With all those information, we can actually draw how this system is gonna deform. Like if we move it like here on the left or on the right, what's gonna happen? I define this angle as a phi 1 and the displacement there as delta h, or I can just define it as 1. It doesn't matter. And we see already